Okay, so today what we are going to look at is like a lossless. Okay, so lossless means you want to represent the data as is. Okay, and then so suppose the encoder represents the data. So there is some data. Our data is a bunch of random variables. Okay, so whether you're trying to compress a file or whether you're trying to compress anything else, okay, you treat it as a sequence of random variables. So the bits in the files are random variables. Or if you're going to look at like a text file, the individual letters will be you can think of them as your random variables. Okay, or if you want to, you can even think of the words as your random variables. So what exactly you're modeling is up to you. Okay, but at the end of the day, you have a sequence of random variables. Uh, you're going to represent them with a sequence of bits. Okay, and so this part is what we call as an encoder. Okay, and a decoder reads this sequence of bits. Okay, the decoder knows uh, what the encoder would have done. Okay, so the decoder doesn't know this exact sequence x1 through xn. Okay, but it knows the statistics of the sequence x1 through xn. Okay, so and it knows the speed by which the encoder translates the individual observations of random variables to bits. Okay. Now, given this, in a lossless source coding setup, the goal is that the decoder can look at the sequence of bits and get back what was the original random variables. Okay. Right. So this is the lossless source coding setup. So few things like the statistics of x1 through xn are known. Right? So the individual values, the individual observations of x1 through xn, the actual observations of these random variables, the realizations, they are unknown. And that's what needs to be communicated. Okay. So does this make sense? Okay. And like we said in the last class, the first thing we are going to look at is when x1 through xn are IID. Okay. Right. Then we are going to show that so then what we do is we pay attention to the length of the encoding. Okay. So okay. So we look at a couple of cases. What happens when x1 through xn are IID and what happens when they're not necessarily IID. And we look at something even more important, which I'm not writing right now because it eliminates this assumption. Okay, that the statistics of x1 through xn are known to both the encoder and decoder. Okay, so in that setting, what you assume is that the encoder, so the statistics of x1 through xn is unknown to the decoder as well. Okay, so the decoder just sees this bit stream and needs to get back x1 to xn. It doesn't know what the statistics are. Okay, so that's something we'll look at maybe after we look at the very basic setup. But one thing at a time. The simplest case is of course when x1 to xn are IID. Okay, and in this case, the simplest case of all is when n equals 1. You just have one random variable. Okay, so let's consider like the real baby case. Okay, how do you encode a random variable x? Okay, one reason to look at it is because we'll get some insights into what is happening. And many of that insights extend when you look at larger blocks of random variables. Okay, so here, what we pay attention to, like we said last class, we pay attention to this random variable, which is the length of the encoding of x. Okay, so for example, like maybe x takes on, we'll take the same example like last class. Maybe x takes on values within the set, 4 possible values. There are different probabilities with which it can take on these values. Okay. We'll just use P1, P2, P3, and P4 for these probabilities. Okay. Now, so this means that with probability P1, you observe a value 0.1 for x. Okay. With probability P2, the value is 0.2. With probability P3, the value is 1, and probability P4, the value is 2. Okay. Because it's a probability distribution, these add up to 1. Okay. P1 to P4 add up to 1. Okay. So everyone okay with this? Okay, the quantity we are looking at is what we do is like we map x with a prefix free code. Okay, now you can map x to a uniquely decodable code as well. So just to recap, prefix uniquely decodable and prefix free refers to the fact that when you look at sequences of random variables, okay, so you have multiple observations. Okay, so then you can uniquely decodable codes, you can parse the concatenation of these code words uniquely. Okay, when you have prefix free, unique decodable comes for free. Okay, and it's even more structured. You structure them as leaves of a tree. Okay, so is everyone completely clear about uniquely decodable and prefix free codes? Okay, so but just for completeness sake, okay, so this is from last class. An example of a prefix free code is 10. Right, so this is prefix free. Okay, a uniquely decodable code. So prefix free codes are automatically uniquely decodable. Okay, so if you write two or multiple code words one after another, okay, there is only one way to interpret this sequence. You don't need the commas. Okay, so if for example, if you concatenate code words, that means I write 100, 101, 011. It doesn't matter how I concatenate. Okay, there is only one way to interpret the sequence of bits as a series of code words. Okay, you'll notice that if you try interpreting it as a sequence of code words, okay, the first code word has to be 10. One is not a code word. Okay, so you look more, 10 is also not a code word. And then you look at 3 bits, 100, so that is a code word. Okay, 101 is your next code word. Okay, and 0 is your next code word, 11 is your next code word. You don't need these commas. Okay, there's automatically only one way to do this. Okay, right, and uniquely decodable. So the prefix free property is not necessary for this unique decoding. Okay, so you can have uniquely decodable code words. Okay, so here uniquely decodable means, I mean, they're not necessarily prefix free. Okay, but you could have a code which is which again like satisfies the same property. If you concatenate code words, there is exactly one way to interpret it. Okay, like let's just try modifying this to, so let's take 0. This one shot. Let's try again. So let's start with 0. So this is 1, 0. And let's see if okay. So here, so let's just, so I'm just doing a little bit of trial and error. So let's see if this can be uniquely decodable. Okay. So the idea is like no matter how you concatenate code words, okay, you should not you should not be, there shouldn't be a problem with parsing it. Okay. Now here the only danger is, so all these, so if a code word starts with a 1, okay, so let's check, like if you if anywhere in your sequence you see exactly 1 0, okay, sandwiched between different ones, then that 0 can only come from these two. Okay, the only worry is what happens when you see a string of zeros. Okay, now when you see a string of zeros, so that cannot come from any of these. Okay, so right. So that results like what happens when you see strings of zeros. Okay, so now we worry about the ones. Okay, so if you see ones, so even ones followed by odd student zeros, and it's the okay. So let's the worry is like if you have okay, let's see like if you have a string of even number of ones uh, and yeah, so in the, right, so if you have an even number of ones, it could be the last pair of ones could be from either this or this, and then you worry about what happens after. So then, yeah, so then if you look at how long the sequence of zeros is, if it is odd, the last one has to be this in the previous block. Otherwise it has to be 1 1. Okay, so if it is an even number of ones, you understand what is happening. If it is an odd number of ones, then you have a bunch of, for an odd number of ones, there's only one possibility. It has to be a bunch of 1 1s followed by an instance of this. Okay, so this is a code that is not prefix free. Okay, 1 1 and is a prefix of 1 1 0. Okay, so it doesn't satisfy the property that no code word is a prefix of another. Okay, so this is not prefix free, but you will be able to decode it properly. Okay, right. So in general, uniquely decodable codes are more general than prefix free codes. Okay, but we'll see that we really don't need to worry about uniquely decodable. They, in terms of code word lengths, okay, they won't add anything substantially new. Okay, so if there is a prefix-free code with a set of lengths, okay, or sorry, if there's a uniquely decodable code with a given set of lengths, L1, L2, L3, and L4, there's also going to be a prefix-free code with those same lengths. Okay, so might as well just work with prefix-free codes. Okay, so technically uniquely decodable is a larger class, but it's a class we don't worry about because it doesn't improve compression. Okay, so right? So the idea is, okay, how do we encode this random variable? So we are going to say that we are going to assign to each of these possibilities, point 1, point 2, 1, and 2, a code word, okay? And without loss of generality, like we are going to assign them code words from a prefix-free code, okay? Okay, so we're going to assign code words from a prefix-free code, and let's say that the code words are L1, L2, L3, and L4. Okay. Now we know that you can think of the code words as leaves of a tree, and mathematically what it means is that 2 to the minus L1 plus 2 to the minus L2 plus 2 to the minus L3 plus 2 to the minus L4 must be less than or equal to 1. Okay, so we saw last class that Okay, and this is the thing is like if I told you, okay, just for fun, that assign these code words from a uniquely decodable code, okay, then your code word lengths would satisfy the same inequality. Okay, so whether they are prefix-free or uniquely decodable codes, the code word lengths will always satisfy this inequality. Okay, so the inequality for the prefix-free codes comes from wrap. When you use this inequality for uniquely decodable codes. Okay, so that's a little more complicated to prove. Okay, but that's called Macmillan's inequality. So people generally call this Kraft's inequality or Kraft-Macmillan inequality. Okay, so but the point is, these code word lengths cannot be arbitrary. Okay, when you say this, sum of these has to be less than 1, you can, the intuition is that none L1, L2, L3, L4, they cannot all be too small. Okay, if they are very small, these are large numbers. Okay, if these numbers become too large, then this sum will exceed 1. Okay, so in a way, like this is saying that your length should at least be this long. Okay, you can make some lengths short. Okay, but if you make some lengths short, the other lengths have to proportionally increase. Okay, so that's why you can say this as like a formalization of the constraint that if you want a prefix-free or a uniquely decodable codes, there's a penalty to choosing short code lengths. Okay, every short code length, if there is one code length with length 1, that takes up 2 to the minus 1, that is 1/2. Okay, you cannot have, if you want to take 4 code lengths, right? If you have one with length 1, the others can't, I mean, clearly there cannot be one more with length 1. Okay, it won't satisfy the prefix-free condition, but in fact, the others have to be longer as well. Okay, so does this make sense? Okay, so right, so the idea is like in order to encode X, okay, you assign these code words. Now, how good is this assignment? The metric to measure how good the assignment is, is to look at the expected code length. So here we look at the expectation of the length of X. Okay. So L of X, remember, it is the length of the code word assigned to X. Okay. So in particular, here the expectation for our particular example, the expectation of the length of X is P1 times L1 plus P2 times L2 plus P3 times L3 plus P4 times L4. Recall that P1, P2, P3, P4 were the probabilities assigned to each of these realizations. Okay, so this would be the expected length of the code word. Okay, now obviously, like something which has high probability should be assigned shorter code lengths. Okay, realizations that have low probability, okay, you can assign them larger code lengths. Okay, now what we are going to show is that this will always be greater than the input. Okay, your expected code length is always going to be greater than the entropy. Okay, so the and this makes it very formal. We saw entropy is the amount of information that you get when you observe a random variable. Okay, so it's the information that you acquire when you observe a random variable. Okay, so if an encoder has represented this with a code word, okay, with some code word assignment, when you see the code word, you do acquire the information that corresponds to observing the random variable. Okay, so this particular theorem, like the source coding theorem, it kind of quantifies it very concretely. Okay, so what you mean by acquiring information when you see a random variable is something like this: represent the random variable by a code. The code length is exactly the number of bits in the code length is exactly what you acquire. Okay, so we are going to so the proof of this is actually very simple, and it has to do with the same techniques that we use, like convexity and the log sum inequality. So we are going to say, okay, the expectation of the length of x in general is over all possible realizations in x. Okay, so we are going to prove it for random variables that take only a finite number of realizations, but this is true in general. Okay, so even when the number of realizations is not finite but countable. Okay. Okay, suppose x takes values in the set x1 through xn. The probability of observing any particular symbol in this set is any symbol xi in this set is pi. Okay? Then the expected length of x, the expected length of the encoding of x is the summation. Sorry, let's also say that. Okay, so we are going to, the length of the code word assigned to xi, we'll define it as li. Okay, so li is just a number. Okay, multiple code words could have the same code word. Okay, then the expected code length summation pi li. Okay, the expected code length is the average of all these lengths, the weighted average of all these lengths. Okay. Now what we are going to do is, like, we are going to look at the expected code length minus the entropy. Okay. And this is going to be summation pi li minus okay. Right. And this is, so we are going to write li, okay, as log of 2 to the li. So remember, logs are to base 2. All logs, if we don't say anything, it's to base 2. So we are going to write li as log of 2 to the li. Okay. So this becomes summation pi log of okay. I'm going to write this as summation pi negative log 1 over pi is just pi. Okay. So this is right. So 1 over 2 to the li is just 2 to the minus li. Okay. And because it is minus sign, it's now in the denominator. Okay. Now this looks very much like a tail divergence. Okay. P is a probability distribution. Okay. But not necessarily 2 to the minus li. Okay. So, but we can come up with a new probability distribution. Okay. Consider this probability distribution. Okay, so the quantities 2 to the minus li, I normalize them to make them into a probability distribution. So here is like, so this one comes as a step in the proof, but it's actually a very fundamental way of thinking. Every time you have code word lengths, you're thinking of a probability distribution. Okay, and the code word lengths map to the probability distribution in this way. Okay, now of course, this goes without, so there's a qualification that is always in force that the code you're thinking about is a prefix-free code. Okay, now this equivalence, if you're not looking at uniquely decodable codes, okay, this qualification, I mean, this insight doesn't hold anymore. Okay, but if you're looking at uniquely decodable or prefix-free codes, okay, the code word lengths, whenever you look at the code word lengths, you're thinking of a probability distribution. That probability distribution is 2 to the minus li normalized. Okay, now, right, so does this make sense? Okay, now this is a probability distribution because all these things are, so each of these, 2 to the minus li is less than 1. Okay, so this is less than summation of 2 to the minus li. So all these quantities are, so this ratio is also less than 1. Okay, they are clearly greater than 0. Okay, and they sum up to 1. Okay, so does that make sense? Okay, so now when you look at this new probability distribution, okay, right, so I'm going to write this. Right, so now 2 to the minus li is qi times this denominator. Okay, so just to make my life easier in notation, I'm going to write n equals summation of 2 to the lj.
That sounds one only when you have like all of your bits allocated correctly, right?
Right, so it is 1 when they're the root, when they're the leaves of a full binary tree. Okay, so when they are not the roots of the leaves of a full binary tree, it will be less than 1. So we'll see that. Yeah, so that's a good question. Okay. So m is this denominator here. Okay. So this is 2 to the minus li is just qi times n. Okay. Here is the probability distribution. Right. So here I have pi over qi plus okay. Now in the second summation, m does not depend upon I. M is just the sum of all 2 to the minus li over all coordinates. Okay. M doesn't depend upon I. So this second summation is just log 1 over m because summation of pi is 1. Okay. Okay. Now two things. The first term is the KL divergence between P and Q. Okay. That is KL divergences are always greater than or equal to 0. For the second term, so from Kraft's inequality, right, m is less than 1. From Kraft's inequality, 2 to the minus code word length summed over all code words is less than or equal to 1. So m is less than or equal to 1. Okay, 1 over m is greater than or equal to 1. Okay. So since 1 over m is greater than or equal to 1, okay, log of 1 over m is also greater than or equal to 1. Okay. So this whole thing is greater than or equal to 0. Okay, and we also know when the equality holds. Okay, so the equality will hold when m equals 1 first. M must be equal to 1. So that means that so we'll see what exactly that means. But the m equals 1, we'll see means that the code word should form the leaf of a full binary tree. Okay, but for this to be equal to 0, not only should m be equal to 1, which means that the code cannot be redundant, it should also be that qi must be equal to pi. Okay, for all that. Okay, so you get an equality if and only if first all the pi happen to be numbers of form 2 to the minus 2 to the minus li. Okay, so we call these dyadic distributions. So every pi should be something like 1/4, 1/8, 1 over 2 to the something. Okay, every probability must be 1 over 2 to the something. Okay, and your code should be not redundant. Okay, so that's when you have equality. Okay, so that's when expected code length will be equal to the entropy. Every other case you have an inequality. Okay, so right, so let's just look at what happens when you don't have redundancy. So when is summation 2 to the lj equal to 1? So here, so everyone knows what a full binary tree is. Okay, a full binary tree is it's a tree. It's a binary tree, which means every node has a binary tree is one where every node has at most 2 children. Okay, a full binary tree is a case where every node has exactly 2 children or 0 children. Okay, so nothing has one child. Okay, so it's something like this. This is a full binary tree, right? So this is a full binary tree. So every node, so this node has 2 children, this node has 2 children. Okay, these 3 nodes have 0 children. So every node is either a leaf or it has exactly 2 children. Okay, so those are full binary trees. Okay, so when your code works, when your code words happen to be leaves of a full binary tree, okay, Trapp's inequality is satisfied with equality. Okay, when your code words are not the leaves of a full binary tree. Okay, an example of something that is not a full binary tree would be something like this. Okay, so when your code words are the leaves of a binary tree which is not complete or full, okay, then Trapp's inequality is satisfied with inequality. So in this case, summation 2 to the minus L. So here these are the three code words. Okay, so the code word lengths are 1, 2, and 2. Okay, and so 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 2 is 1. Okay, so here the code word lengths are 1, 2, and 3. Okay, so the three leaves have are at depths 1, 2, and 3. Okay, so 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3 is strictly less than 1. Okay, right? So, and this is always true, like when Trapp's inequality is satisfied with an inequality, okay, when it is strictly less than 1, okay, your code is redundant. You could have shortened this code word, okay, and still kept it if it's free, okay. So when you have strictly less than 1 in Trapp's inequality, it just means that your code is redundant, okay. There are some code words you can shorten without losing the prefix free condition, okay. Good. So any questions? Okay. So what we'll do next is, okay, we know that the expected code length is at least the entropy. Okay. But what is more interesting is if the expected code length is always very close to the entropy. Okay. That will mean that we perfectly know what, I mean, our interpretation that entropy is the amount of information acquired has a very physical basis then. It is the code word that you have seen and how many bits are there in every realization. Okay, so we have an inequality in one direction that the expected code length is greater than the entropy. Okay, we also have, we can also show that the expected code length is less than the entropy plus 1. Okay, so the plus 1 comes purely because log of 1 over p is not always an integer. 2 pi is not always 2 to the minus some number, some integer. Okay, so here the idea is this. So we are going to look at a code called the Shannon-Fano code. Okay, and here the primary insight here is that for each, so again let x be a random variable that takes values in once again, like you could do this for countable alphabets, nothing specific about finite. With just finite is technically easier, so we just look at the finite bits. Okay, so x is a random variable that takes values in this set x1 through xn. Okay, and what we are going to do is the following. So let so once again, let probability x equals xi equals pi. Okay. Now, one thing we are going to do is So we are going to define li. So this time we are defining li. Not we are not assigned a code yet. Okay, we haven't assigned a code yet. Okay, but here we are doing something weird. Okay, we are first figuring out the code word lengths, and then we'll assign a code. Okay, so the code word lengths we defined to be log of 1 over pi essentially. Okay, but the catch is log of 1 over pi need not be an integer. Okay, log of 1 over pi need not be an integer. So what we do is like we assign the ceiling log of 1 over pi. Okay, ceiling is the smallest integer that is greater than or equal to a number. Okay, so this is the smallest integer that is at least log of 1 over pi. Okay, now we want to see that these code word lengths satisfy Kraft's inequality. Okay, if they satisfy Kraft's inequality, then we know that they happen to be either the leaves of a full binary tree or like a redundant, they happen to be the leaves of some binary tree. Okay, it could be a full binary tree, okay, but it could also be redundant, we don't care. Okay, but it's the leaves of a binary tree, so that way we can write a prefix-free code, okay, consistent with these lengths. Okay, so let's just compute summation of 2 to the 2 to the minus lj. Okay, so this is 2 to the minus so here is one thing. Li is defined as the ceiling of this. Okay, so by definition it is greater than or equal to log of 1 over pi. Okay, so this is the smallest number, smallest integer greater than this number. So in general, we know that the ceiling is always greater than this. Okay. Right, so since Lj is greater than log of 1 over pi, minus Lj is less than log of 1. Okay. Li is greater than log of 1 over pi. So if I use a negative sign on both sides, I have to change the inequality direction. So minus Li is less than or equal to log minus 1 over pi. Okay. Now summation of 2 to the minus Lj, okay, therefore is less than 2 to the minus summation of 2 to the log 1 over 3j. 2 to the x is monotonic. Right? So okay. Now this one, what is 2 to the minus log 1 3j? So this is just 2 to the log of 3j. Okay, and 2 to the log of 3j is just 3j. This is one. Okay, so these code word lengths satisfy Kraft's inequality. Okay, so that means there's some way to build a prefix-free code. Okay, that is consistent with these lengths. Okay, so we won't worry about how exactly we will build this code. Okay, but we'll just say, okay, we will take the Shannon Fano code to be one of the codes that is consistent, one of the prefix-free codes consistent with these code lengths. Okay. We don't care which one actually, like it's not, so it's a detail that we don't care about. Okay. Now, so the Shannon-Fano code is a prefix-free code consistent with these code lengths. Then let's look at the expected code length of the Shannon-Fano code. Okay? Right, so the expected code length of the Shannon-Fano code is the expectation of the ceiling of log 1 over 3x. Okay, 1 over the probability of x. Now, the ceiling of a number is always less than the number plus 1. Okay, because no matter which number you take, between that number and that number plus 1, there is definitely an integer. Okay, so the ceiling is always less than ceiling of any number, and in this case it's log of 1 over probability of x. It's less than log of 1 over probability of x plus 1. Okay, and actually you can say it is strictly less than in this case too. Okay, and this is the expectation of log of 1 over probability of x. The expectation of 1 is just 1. Okay, and this is the entropy of x plus 1. Right, so actually you can get a strict inequality. Okay. So the expected code length is always strictly less than the entropy of x plus 1. Okay, so this is for one random variable. Right, now when you're looking at a sequence of random variables, okay, here is one thing we can do. Okay, we treat okay, so we are looking at a sequence of random variables. Okay, and in this case, the first situation we are looking at is their IID. Okay, so you're looking at a sequence of IID random variables. So x1 through xn are IID. Okay, and let's say they have common entropy h. Okay, we have the sequence of random variables. Okay, now what we know for one random variable actually tells us quite a bit about this case too. Okay, we just treat this entire sequence to be a single random variable. Okay, just imagine this entire sequence is one random variable. Okay, so it's like so instead of measuring like single numbers, you're measuring like a n tuple of numbers. Okay, really doesn't matter, but we are treating z as one unit. Okay, x1 through xn, the whole thing we are treating as one unit. Okay, instead of single numbers, now you're looking at n tuples. Okay, you can write the entropy of, so everything that we said for a single random variable applies to z. Okay, so from the prior section, okay, we know that you can encode z with a prefix-free code. Such that the expected length of z, okay, is less than h of z, strictly less than h of z plus 1 and greater than or equal to h of z. Right, so this is what we found out from the previous case. Okay, but what is h of z? Okay, h of z is the entropy of x1 through xn. Okay, and x1 through xn are IID. Okay, so this is the expectation of log of 1 over the probability of x1 through xn. Okay, but because they are IID, okay, so this is the expectation of the log of 1 over probability of x1, probability of x2, probability of xn, okay? And this is therefore summation I equals 1 through n, expectation of log of 1 over probability of xi, and this is the entropy of xi, which is n times h. Okay? Expectation log probability of 1 over xi is equal to h. They have common entropy h. Okay, and so every term of this summation is equal to h. There are n terms in the summation, each one equal to h. So the summation is n times h. Okay, so this means that the expectation of log of the length of z is less than h n times h plus 1, and it's greater than n times h. Okay, now so this means that if you're looking at the length of so z is x1 through xn, so this is the code length that you assign to n realizations of this random variable. Okay, now so per realization, so if I normalize this by 1, right? So if I divide by n throughout, okay, why do I divide by n? Because c is x1 through xn, so we are actually encoding n realizations of the random variable. Okay, so per realization of the random variable, okay, the number of bits we use is between h and h plus 1 over n. Okay, and when n becomes large and goes to infinity, okay, the right side also becomes uh, the right side also approaches h. Okay, so when you're encoding the long sequences of random variable, okay, so per symbol encoder, you're going to use h bits to encode it. Okay, so the asymptotically optimal way is to use h bits per symbol. Okay, so does this make sense? Okay, so we'll wrap up with like a little bit of a curiosity. So none of these, the Shannon-Fano code, for example, it's not necessarily optimal. Okay, in fact, like we showed that the lengths of the Shannon-Fano code is typically, we showed that it satisfies Kraft's inequality, but it could satisfy Kraft's inequality even with a strictly less than. Okay, so it's not even the least of a full binary tree. Okay, so it may even be redundant. Okay, but it is essentially optimal in the sense that it's only one bit away from the entropy. Okay, and when you're thinking of encoding long bits of sequences with this Shannon-Fano code, okay, then you're doing essentially optimal things. Okay, and here is like a point to note. Okay, if you're encoding 10 realizations of a random variable with the Shannon-Fano code, it's not the same as encoding each one separately with the Shannon-Fano code. Okay, that's not what it is. Okay, what you do is you write the probability distribution, the joint probability distribution of all these random variables taken together, okay, and use the Shannon-Fano code on those probabilities. Okay, so it won't be the same as individually. If you have 10 symbols, you don't encode each symbol separately with the Shannon-Fano code. Then you pay a penalty of almost 1 bit per symbol. Okay, that's too bad. Okay, but when you look at the joint probability of all of them together and use the Shannon-Fano code, okay, then you pay a penalty of only 1 bit for the entire block. Okay, but this also means that you can't split the code word into subsections and say, okay, this is the code word of this symbol and so on. Okay, you need to wait for the entire block to come in before you can decode. Okay, so many flaws in actual encoding. So the Shannon-Turner code is like a way to think about the equivalences between code words and probabilities, but it's not something that we actually use to encode. Okay, except in cases uh, where we can show a priori that it's okay. Okay, but uh, but there are other techniques that are more. One of them that we are looking at today is the Huffman code. Okay, the Huffman code is optimal. Okay, so there's no other code that can do better, and it's essentially a greedy construction. Okay, and then there is the arithmetic code, which is not optimal, but it allows for many nice properties. Okay, so you don't have to wait for entire blocks before you start encoding, and you can, if you partially observe the arithmetic code, you can partially reveal the sequence of symbols that you saw. Okay, so we look at the Huffman code today, like it's uh, essentially because it's so simple. Right? So the Huffman code is essentially a greedy construction. It just notes that shorter probabilities, smaller probabilities get longer code lengths, and longer probabilities should get, larger probabilities get shorter code lengths. Okay. So essentially a greedy algorithm built on this idea. Okay. But it's built in a way that you can also prove that this will be optimal. Right? So here, like, let's give me like 4 or 5 probability. Actually, let me. Uh, so let's say, so for the Huffman code, we first arrange the probabilities in descending order. Okay. So let us say that the probabilities are 0.75. Let's do 0.4, 0.3. Not so interesting. Okay. So I'm just trying to come up with an interesting combination. Point 3, point 4, 6. Okay, so you basically sort them in descending order. Okay, now what you do is we'll construct the binary tree corresponding to the prefix code. Okay, so the way we are going to construct is like we are literally going to make the binary tree. Okay, now what we pardon? 0.3, 0.4, 0.5. Okay. Okay, so right, so here is what we do. We pick these 2 smallest probabilities. Okay, and join them into a node. Okay, these are, so the two smallest probabilities are 0.1 and 0.1. So we join them into a node. Okay, nothing else changes in this step. Okay. Right? In the next step, you do exactly the same thing. Okay, so here, in the next step, we need to sort them again. Okay, so what you do is now you join these two into a node. Okay, 0.15 are the two smallest probabilities now. Join them into a node. Okay, and what you then do is, so this is 0.3. Okay, then what you do is, in the next step, you have this 0.5, 0.3 and 0.2. The two smallest probabilities are 0.3 and 0.2. So you join these into a node. Okay, and then you join this till you get 1. Okay, so the tree construction for this would be like, so you start with here. Okay, this is 0.5, so this is this node 0.5 corresponds to this symbol. Okay, now the second node, okay, so the bottom node splits into these two. Okay, so this is the 0.2 and this is 0.3. Okay, and the 0.3 splits into two more. Okay, and this 0.2 splits into the 0.1. Right, so this will be our tree. Okay, so the code words we assign to this one is, I mean, you can say one is either up or below, that doesn't matter, doesn't change anything. So the code word assigned to the symbol with probability 0.5 is 1. This is 0, 1, 1. Okay, so you read backwards as you go along. Okay. 0, 1, 0. 0, 0, 1 and 0, 0, 0. Okay, so these are the code words you assign to the various symbols. Okay, so does this make sense? Okay, it's essentially a greedy construction where you basically combine the two smallest probabilities at every step. Okay, if you have a choice of multiple, you have a multiple choice. Okay, so if there are three probabilities that are exactly the same, you could combine any two. It's not going to make a difference. Okay. Okay, so this is the Huffman code. Okay, and this one, so the Huffman code is optimal. So this, given a set of probabilities, this is the best. This is the code word with the smallest possible code length, expected code length. Okay. Now, because of things that we have said before, we know that the expected code length must be greater than or equal to the entropy. Okay. We also know that the expected code length here is less than entropy plus 1. Why is it? Because this is optimal, and because this is optimal, it has a smaller expected code length than the Shannon-Fano code, which has a code length less than entropy plus 1. Okay, so the Huffman code has expected code length between entropy and entropy plus 1. Okay. So, and what we know is that this is the optimal code. Okay. No matter how you construct code, you cannot beat the Huffman code in terms of the expected code. Okay. This is also a complicated procedure. So when you're analyzing something, okay, it's almost always easier to use like the Shannon-Farmer code. Okay, that's only when you're thinking. So when you're implementing, okay, the Huffman code is actually used in practice now in many of the, I think maybe in BZIP, either BZIP or GZIP, one of the compression tools like the Huffman code is used. Okay, but a more popular choice is something called an arithmetic code, which we'll look at next class. Okay. Uh, okay. So any questions? Okay. So we'll stop here. So, but you can I'll stop recording, but you can continue asking.